Let's turn our attention for a little bit here to angular motion. And what I've got drawn here is a line in the positive x direction, and that's going to correspond to an angle of 0 degrees or 0 radians. And at a later time, this line might rotate, and we'll say in the counterclockwise direction. And that's going to get us to a new angle, theta, that's not equal to 0 degrees. Now, one of the things we want to point out is that the counterclockwise direction is a delta theta of greater than 0. That is to say, this is a positive change in the angular motion. All right, so if I've gone through a delta theta, some value of delta theta, and I've done that in a certain amount of time, then I must be able to associate with that an angular velocity. So delta theta is an angular displacement, and the positive direction, much like a positive x or a positive y, is in the clockwise direction. So we might say that positive x is to the right and negative x to the left, and that's our convention. Positive y is up and negative y is down. But now we're going to say a delta theta, or a positive theta direction, is counterclockwise, and a negative theta is clockwise. And this really goes back to the right-hand rule. If you curl your fingers in this direction, your thumb is going to point out of the screen, if you will, or out of the board. So your thumb is coming at you. And that's the positive direction, the positive z direction. Keep in mind, if x is this direction to the right, positive y is up, then z is coming out of the page as best as I can draw it in a two-dimensional surface. And so when I go from x to y, that's in the counterclockwise direction. Curl my fingers in that direction, and z is coming out. Or you could put your thumb in this direction, pardon my artwork, and your forefinger in this direction, then your middle finger is going to point in that direction. So of course your other two fingers are curled up here. And so here's your thumb. That represents the x-axis. This is your pointer finger or your forefinger. That represents the y-axis. And then your largest finger, your middle finger. Yeah, I'm not going to say it. Your middle finger is going to correspond to the z direction. That's the right-hand rule, and all of these are at right angles to each other. Okay? So x cross y gives you a positive z. So that's the idea behind the right-hand rule. So we consider a clockwise direction to be negative theta and a counterclockwise direction to be positive theta. All right, so theta is one-dimensional when you think about it. It's either clockwise or counterclockwise, positive and negative. It really is a one-dimensional measure. All right, so theta is an angular position. Delta theta is an angular displacement. Well, all of the definitions that we used before for linear position now have a corresponding angular values. All right, so omega is an angular velocity, and it is by definition the derivative of angular position, theta, with respect to time. Again, definition, I use 3 bars in my equal sign. So this is an angular velocity. And a positive angular velocity would indicate motion in the counterclockwise direction. A negative angular velocity would indicate motion in the clockwise direction. Theta dot then is the dot notation that we've used before. Alpha then is the derivative of angular velocity with respect to time, and so it's an angular acceleration. It's an angular acceleration. And so that's omega dot or theta double dot, second derivative of angular position with respect to time. Right? Second derivative of angular position with respect to time. That's by definition. Now, angle is dimensionless. Angles have no dimension. They can have units, like degrees or radians, but they have no dimension. No length, no time, no mass. But t does have dimension. So d theta dt is 1 over time. Theta has no dimension, so I put a 1 up there. But t is a time. In the metric system and in the English system, this is 1 over seconds, or seconds to the minus 1. We might write radians per second, but radians is dimensionless, so that's okay. You could have degrees per second, but something that's actually more common would be RPMs, and that's revolutions or rotations per minute. That's an angular velocity, not the unit that we prefer, but we use it quite often, so it is a very common unit. Angular acceleration, similarly, is 1 over time squared. You have 1 over time in the numerator, time in the denominator, so that's 1 over time squared. This might be 1 over second squared in the English system, or seconds to the minus 2, not minus 1, but minus 2, or radians per second squared. Those are some of the dimensions that you might see. Now, one of the things that we're kind of interested in is how angle is going to be changing over time, let's say. So what I want to do is I want to look at a vector pointing to the right. And for the sake of argument, I'm going to call this vector u. And I'm going to put a little caret over the top. This is going to be a unit vector. All right, now your book uses u, as we'll see here in a little bit. I don't really prefer u. I'm going to use it just for a little bit. But let's say that that unit vector is pointing to the right, but then later on, it's not pointing to the right. Now, it still has a length of 1, but it's traveled through some angle delta theta, right? It's traveled through an angle or a displacement delta theta. Now, what I'm interested in, let me call this u1 and u2. These are unit vectors, position 1 or the first unit vector, and then it moves to the second unit vector. So delta u, unit vector, is u2 minus u1. Now these are still vectors. They're unit vectors, but they're still vectors. And so here is another vector. Let me actually do this in red. There's another vector leading from u1 to u2. And I'm going to call this delta u hat. Now it's not necessarily unit vector, but it's the change in the unit vector. So I might write u1 plus delta u hat equals u2. Now we know that from geometric addition of vectors. This plus this gives me that. We've seen that before when we added vectors. Geometrically or graphically might be the term that you use. And so u1 here plus delta u is the same as u2. All right, now that's really nothing more than I've already said right here. I've rewritten it here again, and you can see algebraically it's easy to go from one to the other. No problem. All right, so what I'm interested in is what happens as I take delta u and divide by delta theta. And more importantly, what is the limit as delta theta approaches 0 of this delta u delta theta? Now you remember this from calculus. This is the derivative of u with respect to theta. I'm taking the derivative of a unit vector with respect to theta. Well, let's see what happens. Here's a relatively large delta theta right here. But let's go to a smaller delta theta. So I'll just redraw the triangle. So there's delta u hat. There's delta theta. Okay. Now this angle has gotten smaller. How many degrees in a triangle? Well, all triangles are 180 degrees. And this triangle is isosceles. I know it's isosceles because this is a unit vector, this is a unit vector. So those two sides are the same. Well, if that's the case, then this angle and that angle are also the same. And let's call those angles alpha, just for the sake of argument. Well, so if everything adds up to 180 degrees, then alpha plus delta theta equals 180 degrees. All right? But now if you think about it, let's go to an even smaller delta theta. Here's delta u in this situation. Not the best drawing. Let me redraw that real quick. Here's delta u. Here's delta theta inside of here. And what do you notice about my angle alpha? This alpha and this alpha, well, they've gotten bigger. Delta theta is getting smaller. So as delta theta goes to 0, alpha plus alpha equals 180 degrees. 2 alpha equals 180 degrees. Therefore, alpha must be approaching 90 degrees. Let me not say equals. Let me say approaches. Alpha is approaching 90 degrees. So delta u is approaching something that's perpendicular to u. All right, so keep in mind, this was u1. Oops. This was u2. This was u1. This was u2. And so as delta theta approaches 0, we end up with a vector that is approaching 90 degrees to u. And so what I can say then is that the limit, going back to this line, the limit as delta theta approaches 0 of delta u over delta theta. As that gets smaller, that's a derivative, and this is going to be a vector perpendicular to u. It's going to be a vector perpendicular to u. But what we want to keep in mind is this. This vector is the derivative of a unit vector. Now, the unit vector never changes size. The unit vector never changes size. But this vector is definitely changing direction. So really what we end up getting here is a u perpendicular. In other words, a unit vector perpendicular to u hat. All right, that's going to be very important here in just a little bit.